Perfect. All right, so today, guys, I have a beautiful lesson. Very similar to what we did on Friday, except that this time, goodness gracious. This time, we're not going to see our figures on a coordinate plane, okay? So they're gonna be just given to us, and then we're gonna figure out how to justify if they're similar or not, according to their properties. So let me go ahead and give you guys your printout for today. All right, so justifying properties of similar figures. So what we're gonna do is we're gonna be presented with several figures. Now, my question is, or my statement for today is basically being able to identify how do we have similar figures and where do they exist. Now, in the real world, obviously they can exist in nature, they can exist in photographs, in anything that we create basically or recreate, because we're gonna have your pre-image and then your image that has been transformed somehow, and it's gonna be dilated and it's gonna be either enlarged or reduced depending what the dilation has happened. But the way that we're gonna go ahead and see how similarity is present is that we're gonna have the same figure and it's gonna be replicated again. Now, how do we know that two figures or two items or two living things are exactly similar to each other? How do you know? Visually, what would be something that you would look at and see like, they're the same figure, they're just basically different sizes? By patterns, by angles, by sides, by its figure, its structure, the way that it's structured. Now, how about when something's not similar? Would you be able to tell something is not similar to each other? Yeah, okay. Now, the way that we see things here, my first image, I have two beautiful butterflies, same species. They're just basically one's, I think, an adult, and one is basically a dwarf or a little smaller size or a little smaller species of it. Now, my bottom figure here, I have like a succulent that just keeps on reproducing that same figure or that same part of the plant over and over again. But again, it's growing in different sizes as it's going through its process of life, right? Now, over here, we have our triangles, and notice that they're like little triangles all put together. They're like little fractals of each other. And create that larger triangle that it creates or it's composed of. Now, like when we saw the figure, if you guys remember that video that I showed you guys during our first week back, the golden ratio or the golden rectangle, again, that same figure is reproduced over and over and over again. So here we can see the largest rectangle, and then it's reproduced again. And then it's reproduced again and again and again and again and again, keeping that same ratio, that same similarity between the two or the other figures that it's shown. It's again present in nature, it's present in your body, it's present in many parts. Now, whenever two items are not similar, how can we tell they're not? Here we have three examples. We have diagram 1, 2, and 3. Which ones do you see that are similar and which ones do you see that are not similar? 1 and 2, and which one's not similar? 3. Why is it not similar? It's wider. Some people say it's fatter. Something's wrong with it visually, right? We're able to identify that it's not similar, even though it's the same shape. That same little icon, that walking pedestrian, I'm assuming from the street signs, and most you guys are driving. You guys are looking into your little driving book. But we can see that indeed, first diagram and the second diagram look similar to each other. Now, in order for us to identify or verify, we're going to go ahead and see the properties right now mathematically. The third diagram, it looks a little bit off, right? It looks a little skewed, a little slanted. Something happened to its dimensions while it was being basically reproduced. So that's the way that we're going to go ahead and analyze the figures, by looking at the properties of them and looking at the sides, mathematically proving that they are similar or they're not similar. Okay, not just by looking at it and saying like, oh, they don't look similar because one is fatter than the other one. No, we're gonna go ahead and mathematically prove it. So another way that it's used, obviously, in graphics, you have your first image right here, and the second image, it looks a little bit off, right? The same thing happens whenever you copy and paste your figures and then you change the dimensions of it and you only change one ratio or one orientation of the other, or basically you only reduce it one side. So again, they're going to look a little bit off. So with that said, ready to put this into place? Let's go. So we have our properties. This is what we're going to go ahead and examine. We have two things and two things only. We're going to compare sides and angles, like always. Now, my beautiful angles that I'm going to be comparing here are the corresponding angles, and we're going to go ahead and identify which ones they are from the given figures. And we're going to go ahead and see if they're congruent. If we can state that they are congruent, then we have half of our properties basically given. The other half are by comparing and contrasting the sides. And this is where it gets fun, because the sides are not congruent or don't have to be congruent. They have to be proportional instead. So last time, whenever we had congruent figures, we had to have congruent angles and congruent sides. This time we just have to have congruent angles and proportional sides instead. Now, what does it mean to be proportional? We're going to go ahead and create a ratio from the first figure to the second figure. We're going to go ahead and be defining which one's the first one, which one's the second one. And then we're going to be going and creating our little ratios. So comparing and contrasting all the ratios that are present from the sides, and then determining if they are similar or not. If the ratios are congruent to each other, then indeed we do have a beautiful similar figure to the other one, in addition to having the angles congruent to each other. Okay. All right, does everybody have this? 1, 2, 3, 4, 5. Okay. Listos. So what are two things that we're looking at? Angles are congruent and sides are proportional. We're going to see if those two things are true. Okay. Now, let me go ahead and go through this presentation. Like last time, guys, we're going to go ahead and use, where's my presentation? It disappeared. We're going to go ahead and be using similar, or the similarity symbol, to know that two items are similar. So basically, we're going to have triangle ABC is similar to triangle X, Y, and Z. We're going to go ahead and use that little, I know in Spanish you call it tilde, but it's a similarity symbol here in math. Okay. Okay. All right. Let me show you guys the next item. So let's go on to example number 1. Okay. State if the polygons are similar. Now, first things first, we're going to go ahead and look at the angles. The angles are congruent, corresponding and congruent. So here we know that all of them are 90 degrees. So they are congruent. Now, the second item that we're going to look at is if we have proportional sides. Now, the way that we're going to go ahead and state its proportionality is that we're going to go ahead and have our first figure. So figure A, figure B, very similar to what we did on Friday. So we have figure A over figure B. And we're going to go ahead and create the ratio. Now, my ratio is going to be one side compared to another side from the second figure that is corresponding to each other. So in this case, we have our first side, let's say 21. And 21 looks like it's corresponding to 6. All right, so let's go ahead and write that ratio. So we have 21 over 6. Let's go ahead and simplify that fraction. 21 over 6. We can simplify by 3. By 3, we're left with 7 over 2. Or it can be 1 and, actually 2 and 1/2. 2 and 1/2. If you guys wanted a decimal value, you can also use your calculators to get your decimal value as well to give you the response. Do I have to have all three responses there? No, guys, as long as you are able to identify one of the ratios, 7/2, 2 and 1/2, or 2 and 2.5, that would be the way that you're going to be able to find the ratio. Now, the second way, yes. 3, oh yeah, 3, sorry, 3. Thank you, guys. 3. All right, now the way that we're going to go ahead and compare and contrast it is that we need to know if the next ratio is indeed equivalent to that first ratio. So let's go ahead and find another pair of sides. So figure A over figure B. So figure A, what other side do you guys want to compare? 14 and, is it 4? Not 6. I'm telling you guys, I'm having like on Mondays. Okay, how do we simplify this one? Divide by 2. Divide by 2. So we're left with 7/2. We already have that same ratio. You can go ahead and make this into a mixed fraction. So we have 3 and 1/2, or 3.5. But since they're both equivalent to each other, do we have similar figures? Yes, they are similar. And you can write your happy face because you proved them that they are similar to each other. Okay, so this is just basically justifying applying the similarity theorem. Okay, all right, ready. Next one. Let's go ahead and practice on the next one. Now, this time we have a different quadrilateral. So last time we had a rectangle, this time we have a different one. And we haven't seen this one yet. Now, let me go ahead and backtrack myself a little bit on parallelograms. Since we have beautiful parallel sides in a parallelogram, these little icons or these little symbols represent that they're parallel to each other. So this angle is 40 degrees. This angle, since we have parallel sides, are considered to be same side interior. So what do we know about same side interior? They are not the same. They're different, but what's the relationship? They are supplementary. They equal to 180 degrees. So if this angle is 40 degrees, this angle has to be supplementary. It has to be 140 degrees. Now, the same thing happens whenever I have my opposite side. So opposite angles are going to be congruent as well. So this one's 40 degrees and this one is 140. So in a parallelogram, opposite angles are congruent and consecutive angles are supplementary. Now, the same thing happens in our opposite or our next figure. So this angle right here is 130, which means that this one is also equal whenever they're adding together are equal to 180. So therefore, this one is 50 degrees. Opposite angles are congruent. So this one is 50. This one's also 50 and opposite angles are congruent. So this one is 130. So let's go through our properties. My corresponding angles have to be congruent. 1. My corresponding sides have to be proportional. Now, what do you guys think about this one? How are they not congruent? The angles are not congruent. So even if we were to find a corresponding angle, for example, this one between 5 and 7, 15 and 21, 40 degrees does not equal 50 degrees. So therefore, my corresponding angles are not congruent. So it doesn't suffice, or it doesn't basically complete or correspond to that first part of our property, where we have to have corresponding angles equal to each other. So therefore, we cannot state that they're similar. So this one is not similar. And you can write your sad face because obviously we didn't prove. We could improve them. Not that we didn't. They're not. All right. Not too bad, right? All right, so we have our sides and our angles. Ahora sí, ready? Here. All right, now let's go on to the next one. State that the polygons are similar. Let's go ahead and see if we have corresponding angles congruent and corresponding sides proportional instead. So let's see. We have this angle right here. Looks like it's corresponding and congruent to this angle, which means that the next one to it corresponding should be also congruent to it. There you go. The next one is congruent to the next one, and so on and so forth. So my angles are congruent. Okay, now let's go ahead and go on to now our sides. Are they proportional? What sides do you guys want to make proportional to each other? Which one do you want as your first figure and your second figure, A and B? So this one is A, and this one is B. Okay, doesn't matter, guys. You choose how you guys want to create your ratio. So figure A, figure B. Now, whenever you choose your enlargement and reduction, it doesn't matter. Okay. All right. So what side do you want to compare first? Gianna, help me out. Which one do you want to compare first? Pick one. From A to B. So from A, which one do you want to compare? Okay, so let's do 15. Let me highlight it very quickly. You're only choosing one of it. 15. And which one's 15 corresponding to? 6. Okay, so let's go ahead and create our beautiful ratio. So here's 15. Here's 6. How can I simplify this ratio? Divided by 3. We're left with 5 over 2 or 2.5. There you go. This is where I got the 2.5 first. Sorry. All right, or 2 1/2. Okay. All right, Gianna, pick somebody. A ver, Josue, help me pick the other figure. Ratio, sorry. Figure A and figure B. Turn it off, guys. A ver, Jose. You pick another side. So pick your first side. Which one do you want to start with? You can choose whichever one you want. So for example, you can start with your bottom one or your sides. 10. Okay, so 10 has to be corresponding to what side of your second figure? 4. Okay, so let's go ahead and create our beautiful ratio. It has to be figure A, so 10 over 4. Let's go ahead and simplify. How do we simplify this beautiful ratio? Divide by 2, divide by 2. And let's see, 10 divided by 2 is 5. 4 divided by 2 is 2. Woohoo! We have our same ratio. 2 over 5, 2.5. All right. And the last pair of sides, guys, by default is what? 40 and 16. So let's go ahead and do that last one just to verify that it's also proportional on that side. Let me do it right here in the middle because I ran out of space below. So figure A over figure B. So what goes above? 40 over 16. What can I simplify these two by? I can simplify them by 8. You can by 4, but then you would have another factor to simplify them by. So we have here 5 over beautiful 2. All right. So do we have similar figures here? Yes, we do. So similar. And your happy face because you proved that they're similar. All right. How do you feel about these now? Good, okay. Let's see if number 4. Let's go ahead and try number 5, guys. Go ahead and skip number 4. Let's do number 5. Number 4 is from tomorrow. Let's go ahead and determine whether the polygons are similar or not. Go ahead and try these 2 on your own. Let's see if you guys can do it. We have our first one. We have a beautiful parallelogram. And our beautiful, will look to be trapezoids on the second one, or quadrilaterals. Let's see what you guys get. Pass it on, Brian. Let's see if you can help me with the second ratio. All right, Jose, help me with the second ratio. Let's see. So it's figure A over figure B. $20 and $5. 20 divided by 5 is 4. So do I have beautiful similar figures? Yes, I do. So these are similar. All right. Jonathan, right after the return. So you selected 9 and 15. 9 and 15. So this means that this is figure A, this is figure B. Okay. And this is divide by 3, divide by 3. We're left with 3 over 5. All right, pass it on. Nelson, what's another figure that, or another pair of sides that we're gonna go ahead and compare? Figure A, 42 and 80. So what do we divide by? Let's start with 2 if you can figure out a value. So 2 and 2. This would be 21 and 40. I don't think they have anything more in common, but can you find the decimal value of 21 and 40? Do you have a calculator? What's the decimal value, guys, of 21 and 40? It should be something less than 1. What is it? I couldn't hear it. 0.529. I can't hear you. 0.25. Ay. Now, in this case, do we have 2 equivalent fractions, guys, or 2 equivalent ratios? 21 over 40 and 3 over 5. Are they equal to each other? No. So therefore, are these 2 figures similar to each other? No, even though they seem like they are, they're not similar. Now, if it's hard for us to identify whenever 2 of the fractions are equal to each other, always convert them into decimal values. So for example, 3 over 5 should be a little bit more than half, but not exactly or very close to 0.5. So when that's the fact, or when that's the case, we can go ahead and create them or make them into decimal values so we can go ahead and identify if they're congruent or not. All right. 20, 35. 21 and 35. So 21 and 35, you can simplify this by, which one's my first figure? Hold on. It would be, yes, I did it right. Okay. So divide this by 7. We're left with 3 over 5. These 2 are the same, but notice here that we have the 4 sides. I mean, so we have to do the four ratios. So as soon as one pair of sides is not congruent to the other ones, that's it. So if we're given different values like this one, we have to try them all out. And they all have to be equivalent to each other. Just how we did it, I think it was on the second example, was it the second example with the trapezoids? Where we had the 3 different sides or the 3 different pair of sides. Okay, so that was a good question. Okay.
One for the other one, you have to like divide B over A and now it's like A over B.
It depends on what your ratio is. So for example, the other one, we're trying to get the scale.
Oh.
If
But
you're
if-
trying to get the scale and the order of which one your first figure was, your pre-image and your image, it does matter. Here, as long as you're able to identify your scale or which one you're comparing to, it doesn't matter.
Hmm.
Okay,
So can I still do like?
you can
B
still
over-
do a B over A if that works for you. Okay, any questions on all of this, guys? Let me go ahead and give you guys your homework so you guys can have it.